This is the continuation of the last video. In the last video, we covered whole life assurance and we looked at the expectation of the present value and the variance of the present value for both end of year of death policy and immediately on death policy. Now in this video, our aim is to look at term assurance. So if you remember, term assurance is nothing but, suppose you buy the policy at age X and the term is n years, so this is X plus n. If you die within this duration, your nominee will get the money, that is death benefit as per the policy. If it is end of year of death, then the nominee will be paid at the end, and if it is immediately on death, then right after your death the nominee will be paid. All right, now let's look at the present value. And since we are considering the integer ages, so this is end of year of death policy, so we are going to focus on discrete random variable. So if kx equals to 0, now this means the person will not even survive for 1 year, right? So the present value is v, and if kx equals to 1, so the present value is v square. If kx equals to 2, present value is v3, and so on. If kx equals to k, then the present value is vk plus 1. And now what if kx equals to n? So in term assurance, the policy will expire at x plus n, right? If you die within x and x plus n, then your nominee will be paid. But if you die after x plus n, then your nominee will get nothing. Okay, now here kx equals to n means the person will survive for at least n years after age x, so the present value is 0. Now what if kx equals to n minus 1? So the present value is vn, right? Because the policy has not yet expired. So we can write present value equals to, now there is condition, if kx is less than n, we can say v to the power kx plus 1, but if kx is greater than or equal to n, present value is simply 0. Now you know we are interested in calculating the expectation of the present value. So this is summation k goes from 0 to n minus 1, v to the power k plus 1, and then PDF, that is probability in discrete, plus summation k equals to n to infinity, and this is 0, so the probability kx equals to k. Now here summation k equals to 0 to n minus 1, v k plus 1, p kx equals to k. Now we are going to use one strategy to simplify the summation. So we are going to add and subtract an extra term, that is kx equals to n to infinity, v to the power k plus 1, so this is the same term, probability kx equals to k, and we are going to subtract this additional term, summation k equals to n to infinity, v to the power k plus 1, probability kx equals to k. Now if you combine these two terms, this is k equals to 0 to infinity, v to the power k plus 1, probability kx equals to k, right? And the last term is k equals to n to infinity, v k plus 1, and then the probability kx equals to k. All right, now we know this is nothing but ax from the previous video minus, now let's expand this, if you remember the PDF, this is nothing but kpx qx plus k. All right, now if you put k equals to n, this is vn plus 1 npx x plus n, right, plus vn plus 2 n plus 1 px qx plus n plus 1, and so on. Okay, now this is as it is. Now let's take vn and px common from this whole expression. So the remaining term will be, now let's look at how we can break these terms. So this is n plus, okay, this term is simple because we have npx, so npx is common, so the remaining term is vqx plus n. Let's see how we can break this term. So this is n plus 1 px. Can we write from the principle of consistency npx times px plus n, right? The person's age is x, will survive for n years, and then again the person age is x plus n, and will survive for one more year, right? This is same. So this is how we can break this. Similarly, for n plus 2 px, you can write npx times 2 px plus n. Okay, so this is how you can break this. So now we can write v square px plus n qx plus n plus 1, and so on. So now this is ax minus vn n px, and we can write this term in the summation, that is k equals to 0 to infinity vk plus 1 kpx qx plus n plus k. Okay, now this is as it is, vn n px, so this is nothing but ax plus n, right? We have x plus n instead of x plus k. So like if you remember from the previous video, we had summation k equals to 0 to infinity vk plus 1 kpx qx plus k, right? Now instead of x we have x plus n, so that's why this is x plus n. Now for this whole term we have an actuarial notation, that is ax 1 and n. So this is death benefit 1, okay, but we write just a simple small vertical bar, that is 1. So this is for the term assurance payable at the end of year of death. Now let's look at the variance of the present value, and you can also understand this from the general reasoning. So let's look at that first. So suppose this is our number line, and this is x plus n. Okay, let's say you want to buy the whole assurance policy from age x. Okay, so from here you want to buy the whole assurance policy, that is ax. So this will be equal to, you can break this. So let's say you have the term assurance for this n period, so you can write ax dash n, and then again you can buy the whole assurance from x plus n. So this is npx, you must have survived this duration, npx vn, because we are calculating the present value, ax plus n, right, from here. Now if you bring this term to the left side, you will get ax dash n, this is equals to ax minus npx vn ax plus n, right? So you can directly get this answer from the general reasoning. All right. Now let's look at the variance of the present value. So the variance of the present value, expectation of the present value squared minus expectation of the present value whole square, and this is summation k equals to 0 to n minus 1 v to the power 2 k plus 1 k p x q x plus k, right, minus a x dash n whole square. Okay, just let v square equals to v1, so I dash equals to 1 plus I whole square minus 1. So this becomes summation k equals to 0 to n minus 1, v1 is v1 k plus 1 k px qx plus k, plus summation, now we are going to add and subtract the additional term, k equals to n to infinity v1 k plus 1 k px qx plus k, minus summation k equals to n to infinity k px q x plus k minus a x dash to n whole square. Okay, so now if we combine these two terms, we'll get k equals to 0 to infinity v dash k plus 1 k px qx plus k minus, and now we can expand this term. Okay, this summation we can expand this, so this is v dash n plus 1 n px qx plus n plus v dash n plus 2 n plus 1 px qx plus n plus 1, and so on, and at last we have x dash n whole square. Okay, now this is nothing but ax operated at I dash minus, okay, we can write this term, so this is ax dash n whole square. Now from this expression we can take the common v dash n plus n px, so the remaining term will be v dash qx plus n plus v square dash px plus n qx plus n plus 1, and so on. All right, so now this is ax at the rate I dash minus ax dash n whole square minus v dash n px. Now what is this? This is nothing but ax plus n operated at I dash. All right, so now combining these two terms, we can say this is a x dash n operated at I dash, and this is a x dash n whole square operated at I. All right, now okay, let me write with different color. Ax dash n is ax minus vn n px ax plus n. We have a different notation. 2ax dash n is 2ax minus v to the power 2n. Please focus here, this is 2n, this is where you can make mistake, n px 2ax plus n. All right, so we can write 2ax dash n at the rate I minus ax dash n whole square at the rate I, and this is the variance of the present value. All right, now let's look at a few more notations. Now in this equation here we can see that although we can calculate this term separately, that is npx is nothing but L x plus n divided by Lx, but here we have to look at a few more values from the table, which can be tedious. So in table we are given a different notations, so let's look at that, and this will simplify our calculation. All right, so dx, this is just a notation, dx is Lx Vx. Okay, we can write dx plus n, which is Lx plus n v to the power x plus n, and if we divide dx plus n divided by dx, this is npx vn, right? Lx plus n vx plus n divided by Lx Vx, so this is Lx plus n divided by Lx v to the power n, and this thing is npx vn. All right, so now you can write ax dash n is ax minus dx plus n divided by dx ax plus n. Okay, now let's look at death benefit payable immediately on death. So payable immediately on death, so the present value will be v to the power tx. Now this is just any point, right? So the whenever you die, nominee will get the money at that point. Okay, so this is not necessarily the integer number, we are considering any number including fractions. That's why here we have continuous random variable, and this is tx is less than n and pv equals to 0 when tx is greater than or equal to n. Now expectation of the present value is from 0 to n vt tpx mu x plus t dt plus 0, sorry, this is n to infinity 0 tpx mu x plus t dt, right? Now 0 to n, we can add and subtract extra terms, tpx mu x plus t dt plus n to infinity. Now you can simply copy this whole term inside this, and then again you can subtract n to infinity and this whole term over here. Okay, so this is simply addition and subtraction of the same term. Now combining these two terms, we'll get 0 to infinity vt tpx mu x plus t dt minus this term n to infinity vt tpx mu x plus t dt. Now here we'll use substitution. Let t equals to s plus n. So from here s is t minus n, and we are also going to differentiate this. So this is ds equals to dt. Okay, so and this term is nothing but a bar x. If you do not remember, then you can refer back to the previous video. So this is 0 to infinity v to the power, instead of t you can write, so this is s plus n, right? S plus n px, okay, and this is mu x plus n plus s ds, right? Now we can simplify this, minus, we can take Vn and Px common from this integration, Vn and Px common, 0 to infinity, Vs s Px plus n mu x plus n plus s ds, right? So this is a bar x minus Vn n plus n Px, and if you remember, this is nothing but a bar x plus n. Okay, and then we can write this as ax. So this is the actuarial notation. All right, ax a bar x dash n, and this is approximately equal to 1 plus I to the power 0.5 ax dash n. Okay, and this is true when death occurs on an average. Okay, let me write, on an average death occurs in between birthdays, and I have talked about this assumption in the previous video, so you can go back and watch that. So the expectation of the present value is a bar x dash n. Okay, this is approximately equal to 1 plus I to the power 0.5 ax dash n. All right, now let's see how we can derive the variance. So the variance of the present value is, okay, I'm going to write down the formula directly, and I leave this to you because the idea is very similar. You will basically calculate from the very beginning, that is expectation of PV square minus expectation of PV whole square, and then you will write the integrations and you will do the further calculation. So I leave this to you. If you're unable to do it, let me know in the comment section. I'll make a separate video for this, but for now I'm just going to write down the formula. Okay, and you can predict this formula. So this is 2a bar x dash n minus a bar x dash n whole square, where a bar x dash n is approximately equal to 1 plus I to a x dash n. Okay, and this is approximately equal to 1 plus I to a x minus v to the power 2n n px to a x plus n. All right, we have a bar x dash n equals to a bar x minus v n n px a bar x plus n, right? If you don't remember this, then you can compare with this. X dash n equals to a x minus v n n px a x plus n. So this is all about term assurance. So now let's stop here, and in the next video we'll talk about other assurance. So I'll see you in the next video. Thank you so much for watching this video.